Want to learn to code? Looking to expand your math skills? Just interested in challenging your mind? Make learning fun by visiting Brilliant. They have tons of interactive courses and you'll learn how to solve new problems in a snap. Brilliant can build your skills in physics, problem solving, computer science, and math. You'll earn a great education by studying hands-on and completing new problems. It's easy enough to begin. Just pick a course you're interested in and get started. Your curiosity will handle the rest. Expand your mind, explain the universe. Visit brilliant.org/explain the universe. I've got one word for you: getaway. Just imagine the sun, the beach, an ice cold drink in your hand. With the American Airlines Advantage MileUp card from Citi, you can go from daydreaming to sunbathing by earning miles on everything you buy. It's the card that turns everyday purchases into Advantage miles, like 2 times miles at grocery stores. Plus, you can even earn a special bonus miles offer after qualifying purchases. Head to citi.com/mileup today to apply for the American Airlines Advantage MileUp card and get closer to that getaway.
Amazon Music and Wondery present Smartless. It's called Smartless as in less smart. Jason Bateman, Will Arnett, and Sean Hayes host this hilarious weekly podcast. Every week, one host invites a celebrity guest, and the other two have no idea who. The guest list has included major stars like LeBron James, Aquafina, Conan O'Brien, Ryan Reynolds, Billie Eilish, and Seth Rogen. What happens is genuinely improvised and authentic conversation filled with laughter and newfound knowledge to feed this smartless mind. Download the Amazon Music app so you can listen to new episodes of Smartless 1 week before it's available everywhere.
Hey Jorge, do you know what you are made out of?
I think I'm mostly made out of bananas and granola and cereal. That's my main diet. What?
All right, well, what's that stuff made out of?
Right. I think it's made out of protons, neutrons, and electrons, right?
Right, and then those are made out of?
Those are made out of up quarks, down quarks, and also electrons.
All right, that's like 99% right.
Only 99%? What's the other 1% of me made out of?
All sorts of weird, exotic particles.
Ooh. Now I feel exotic. You can call me Exotic Jorge, except I don't have any exotic tigers.
Well, it's not just you, it's everyone and everything. It's actually normal to be exotic. Every tiger has exotic particles.
Hi, I'm Jorge. I'm a cartoonist and the creator of PhD Comics.
Hi, I'm Daniel. I'm a particle physicist, and I'm made of the same particles that you are.
That I am? The same, like we share the same particle? I thought my particles were exclusive to me. Are we going to break?
Your electrons and my electrons are all just different wiggles on the same electron field, man.
Oh, we're all connected, dude.
Yeah, we're all just different fluctuations in the same quantum field.
Well, this is me waving at you with a wave function in the same field.
Yeah, you're not just waving at me. You are a wave at me.
We're all waves.
We are all waves, exactly.
But welcome to our podcast, Daniel and Jorge Explain the Universe, a production of iHeartRadio.
In which we wave our way around the mysteries of the universe, talking about the deepest, biggest questions, the nature of reality, what everything is made out of, how it all works, what science has figured out about the tiniest little particles and the largest galaxies and everything in between. We don't shy away from the biggest, deepest, scariest, most interesting questions that define the nature of human existence and the context of our lives. We dig right into them and explain all of them to you.
That's right, because it is an exotic and also quixotic universe full of interesting mysteries and questions and lots of interesting kinds of particles and celestial bodies to think about, to wonder about, and for us to discover.
That's right. It's a crazy, beautiful universe out there with so many weird things, and we would like to understand all of them, not just like 1 or 2 of them or even 90% of them. We want to figure it all out because we want to have a deep, comprehensive understanding of the entire universe. We're greedy that way.
Yeah, physicists are just basically Pokemon collectors, right? You got to catch them all. You can't leave any Pokemon ball unturned.
That's right. And sometimes we want to evolve our particles from the lowest, most boring particles to the weird, exotic forms that we can use to defeat our neighbors.
Yeah, and in this episode, Daniel, we're sort of stretching maybe the limits of these quantum fields because we are more far apart than usual. This is an interesting international version of Daniel and Jorge explain the universe.
That's right. This is Late Night Coast to Coast with Daniel and Jorge.
Yeah, we just need that groovy jazz music maybe in the background. Can we work that in?
But you're right. I'm coming to you live from Copenhagen, Denmark, where I'm spending my summer on a mini sabbatical doing research at the Niels Bohr Institute.
Nice. Niels Bohr, he's a pretty big name in physics, right? He discovered sort of the structure or the initial structure of the atom.
That's right. He had a big role to play in the early derivation of quantum mechanics, which is one reason why it's called the Copenhagen interpretation of quantum mechanics. And here at the Niels Bohr Institute, it's sort of an old-fashioned physics institute. Back in the day, if you had an institute named after you, you were also in residence there. So some of the buildings here at the Niels Bohr Institute are like his apartments. And then later, they all got turned into graduate student offices, some of which have like his bathtub in them.
That's where he yelled Eureka and ran down the street naked, right? Is that the famous bathtub?
That's right.
Or am I thinking of another discoverer?
No, I think every science story involves a bathtub and somebody yelling Eureka while naked. Every single one.
And if it doesn't, it should, because why not?
That's right, because you need the drama. No, it's an exciting place to be. If you've seen the play Copenhagen, that's all about Niels Bohr and Werner Heisenberg's conversations about fission and quantum mechanics during World War II. It takes place here at the Niels Bohr Institute and the park right behind it. So it's a place that's sort of steeped in history. So yeah, it's a nice place to come and do some science.
So are you recording this from Niels Bohr's closet, or are you actually in his bathtub too?
I'm in Niels Bohr's podcast booth, of course. He was a famous podcaster back in the day.
Oh, that's right. You couldn't shut that guy up. He just loved to talk.
He invented everything. Quantum mechanics, structure of the atom, podcasting.
Also, he was the first Instagram star, I heard. First TikTok dancer.
He definitely was not boring.
He's a man of many talents. But anyways, we are here to talk about the universe and try to explain it to you because it is a pretty interesting universe. And one of the biggest questions in this universe that we can ask is, what are we made out of? Like, what are humans? What are people? What are dogs? What are watermelons? What's it all made out of? And Daniel, we've made a lot of progress, not just in this podcast, but as a human species trying to figure that out. And we've broken things down pretty well up to now.
Yeah, I am impressed with how far we have gotten. Several hundred years ago, we knew that things around us were made out of about 100 basic elements, which is already huge progress, right? To describe all those things you mentioned in terms of just 100 building blocks is a huge step, right? It could have been an infinite number of building blocks that describe all the things around us. It could have been that every kind of thing had its own particle. Watermelons could have been made out of little watermelonitos, for example. But in our universe, weirdly, everything can be built out of a smaller set of stuff. So even being able to describe the universe around you in terms of 100 elements is a huge deal. But we have made progress since then, right? We have shown that those elements are made out of just a few smaller particles from which you can make lithium and technetium and uranium, all with the same ingredients. So yeah, we have made a lot of progress. And as you say, it's not just about the universe around us. It's a very personal question. We are asking what we are made out of. What is the recipe for me?
And I like to think that I'm made out of the right stuff. I don't know about you. Or at least the mostly right stuff.
Sometimes I feel like there's a bit of wrong stuff in there, but yeah, mostly the right stuff.
Mostly wrong, right. It is a pretty interesting arc for sort of our journey as a human species to sort of think that there's all this stuff around us that's made out of, that looks really different and looks very varied and wonderfully diverse. But it turns out that as we dig down deeper and deeper, it's all sort of made out of the same stuff. First, it's made out of the same elements and then the same particles. And so right now we have a pretty good picture of where we stand in terms of what we're made out of.
We do have sort of a good picture. We've made a lot of progress, as you say. We boiled it down from 100 elements to just the proton, the neutron, and the electron. And now, of course, we know the proton and neutron are just made out of a couple of quarks. So it sort of seems like, wow, we've really narrowed this down. Everything we are made out of has only 3 basic ingredients. But, there's a twist to this story. As we dig down deeper, we discover that the answer is not quite as simple as we thought. And that some of those other weird particles we see in colliders and in strange exotic cosmic rays from space might also be playing a role in making us up.
Yeah, because I think, as we've talked about in this podcast a lot and people who've read our books, we know that the atoms and elements, they're made out of protons and electrons, and protons are made out of quarks. But you're saying it's a more complicated picture than that.
That's right. It turns out the deeper you dig, the weirder we are.
So today on the podcast, we'll be asking the question, What's inside a proton? Now, Daniel, I assume I'm not going to find tigers, exotic tigers, or bananas and granolas in there.
You might just actually, you might. Tigers and anti-tigers.
Oh, my.
But when I was a kid, I always wondered, like, what were the particles themselves made out of? Like, I had this idea that a proton was like a scoop of particle stuff. You know, it was like a tiny little spinning ball made out of some particle stuff. And really the question was then, what was that stuff? What is like the basic clay of the universe out of which you built these particles? Because that's more interesting than, you know, like the fact that you happen to take a scoop of it to make a proton. So to me, that was always the more interesting, deeper question.
Well, it's kind of interesting that, you know, in high school, we sort of learn about protons and electrons, and then you learn that protons are made out of quarks. And it feels like you call these things particles, but really they're made out of smaller particles inside of them.
Yeah, exactly. Everything is just shells within shells within shells until we get down to the smallest particles we know of, which we think of as tiny little dots, which contain all sorts of weird energy and interactions. So it's sort of like we are made out of Legos, and then those Legos are made of smaller Legos, and those Legos are made of smaller Legos.
So the proton is a pretty basic particle, but I guess the question we're asking today is what's inside a proton? And as we talked about, most people think that it's just quarks inside of them, but maybe there's more to them. So we were wondering how many people out there had thought about what is exactly inside of a proton, whether or not it's just quarks or not. So as usual, Daniel went out there into the internet to ask people what is inside a proton.
So thank you to everybody out there in the internet who is willing to volunteer. And if you would like to participate for future episodes, please don't be shy. Write to us. It's fun. There's no pressure. You'll have a good time and you'll hear your voice on the podcast. So please send us a note to questions@danielandjorge.com.
So think about it for a second. What do you think is inside a proton? Here's what people had to say.
I think it was 3 quarks, but I don't know which ones.
Isn't that 2 plus quarks and 1 minus quark? It's been a long time since I read any of this stuff, so I forgot a lot, but I think that's it.
I know that there are subatomic particles inside a proton. I think you break it open and find, isn't there quarks inside? I can't remember. It's gluons or something. There's something inside it. I don't know.
I'm just going to say, in general, quarks. I know that there's some up ones and some down ones and some strange ones, and I don't know which ones.
A proton, it's a particle, and together with neutron and electron make up the atom. That's it.
I think a proton, being a subatomic particle, is just a oscillation of the electroweak force or something like that.
Well, in a proton, you have 3 quarks. Can't remember if it's 2 up quarks and a down quark or 2 down quarks and an up quark, but there are 3 of them. And from reading, I recently read this really amazing book called We Have No Idea. It's by these guys called Daniel and Jorge. Maybe you've heard of them. I don't mean to name drop. There's a lot of energy wrapped up in the bonds holding those quarks together. So I'm going to go with 3 quarks and a ton of energy in the bonds.
All right. Some pretty consistent answers, I feel. Like everyone who maybe listens to this podcast has this pretty basic idea that what's inside of a proton are basically 3 quarks and some gluons.
Yeah, mostly hands down, people thought quarks and a few gluons to stick them together. There's even a nice plug for a great sounding book in there called We Have No Idea that tells everybody all about the mysteries of the universe.
Oh, yeah? What is this book about? And who are the 2 handsome gentlemen that wrote it?
It was ghostwritten by us, but it looks like it was written by 2 handsome gentlemen. It's all about everything we don't know about the universe, all the big open questions that science still has not figured out, that scientists on the very forefront of knowledge are digging down into the mines of truth to try to understand. It's a fun book all about physics with hilarious cartoons drawn by Jorge, and you should check it out. It's called We Have No Idea.
Yeah, at least one of our listeners read it, according to this sample of responses. But most people seem to have this idea that protons are made out of 3 quarks. So maybe, Daniel, let's start with that. What are the basics of what we know about what's inside a proton?
That's right. The first answer, the sort of best approximate answer to what's inside a proton is exactly what our listeners have said, which is 3 quarks. Right? You take 2 up quarks and 1 down quark, and you put them together and you make a proton. And that's already sort of fascinating and weird because, you know, the proton has charge +1, right? It's the opposite charge of the electron, which is, of course, charge -1. So how do you get 3 quarks to add up to a charge of +1? Well, it means that the quarks themselves have weird fractional charges. Like the up quark has an electric charge of +2/3, and the down quark has an electric charge of -1/3. So you take 2 up quarks for a total charge of 4/3, and then you add a down quark, which has a charge of -1/3, and boom, it adds up to 1, the charge of the proton. And I always thought that was weird, like how exotic to have particles with fractional charges, 2/3, -1/3. How strange is that?
Right. That's weird because like 1/3, it's not a even number. It's like it's an even fraction, but it's one of these sort of infinite numbers, right?
Yeah, it is weird. And you might think, well, you could have just defined the charges of the proton and the electron to be +3 and -3, right? Because then the up quark would have charge +2 and the down quark would have charge -1. So in that sense, you would avoid like any fractional charges. But the weird thing is that we don't see any other intermediate values. Like we don't see particles that have charge 1 2/3 or -4/3 or something like that. We only see integer charges, sort of the macroscopic level, the proton, the electron, the neutron has charge 0, but they are made out of particles that have fractional charges. So they just seem to always add up to these integer values, which is kind of weird.
Yeah, it's weird also that it adds up to like +1, exactly +1, which just happens to be the opposite of the charge of the electron, like exactly the same.
Exactly, because the electron is not made of quarks, right? The electron is made out of the electron. As far as we know, it's not made of anything smaller. So the fact that the quarks add up to exactly +1, which balances the electron, that's totally necessary for chemistry, right? For the hydrogen atom to form. But according to our theory, those are very different things. You're balancing completely different ingredients, and they happen to exactly balance. And in our theory, that's sort of an accident. We have a parameter in the standard model for the electric charge and another one for the charge of the quarks. And there's no reason they have to balance, but they somehow do. And that's a hint, right? That's a clue that says that something is going on here that you haven't really figured out. There's some connection between the quarks and the leptons, the electron, that we don't understand. But that's a mystery for another day.
But I guess maybe the basic takeaway is that inside of a proton, the basics of a proton involves having 3 quarks inside of them, 2 up quarks and 1 down quark, right?
That's the basics. And for most things, it will do. But as soon as you take a closer look, you realize that can't be the whole story. There must be something else going on in the proton, because just these quarks by themselves can't explain the way the proton is.
Really? It has some strange behavior?
Well, first of all, look at the mass of the proton. Like the proton weighs 1 giga electron volt. That's like 1 billion electron volts. But it's made out of quarks whose masses are much, much smaller. They're like 1,000 times smaller. They're a few million electron volts. So how do you make something out of millions of electron volts and end up with 1 billion electron volts, right? That's pretty weird. That's like taking a few $1 million and turning it into $1 billion, right? There's some sort of like stock market magic there. So the proton is much, much more heavy than the things it's made out of, which tells you something else must be going on.
Sounds like a .com boom, which means are we headed for like a universal crash here, Daniel, with the particles?
That's right. Can I interest you in investing in my proton fund? It's not a bubble. I promise you, it won't collapse. The proton is stable.
Yeah, but I think the basic mystery is that, each quark weighs a little bit, but once you put them together into a proton, suddenly the whole thing weighs a lot. And so the question, I guess, the first mystery is like, where does that extra mass come from?
Yeah, like imagine you take 3 Lego pieces and you put them together and all of a sudden the thing you've made is now like super duper heavy. It weighs 1,000 pounds or something. You'd wonder like, whoa, what's going on? And so already we know that there's something else in the proton, something else that's contributing a lot to the mass of the proton. And the number one missing element there, of course, is the thing holding those quarks together. Those are the gluons and the photons that are binding these quarks together. Because remember that quarks are special in a really important way. They feel the strong nuclear force. Strong nuclear force being the strongest, the most powerful, and also the weirdest force in the universe. And it's the source of like fusion and fission and all those crazy sources of energy. It powers the stars. It's the dominant force in the universe, especially at these very short distances. And so to hold these quarks together into a stable particle called a proton, you have to have a lot of energy. And that energy is whizzing around inside the proton in the form of gluons.
Right. So it's all this extra energy inside holding the three quarks together that gives the proton its extra mass. That's kind of how you explain how it has so much more mass than the three quarks.
Yeah. And you have to get away from the idea of mass as just being the mass of the stuff it's made out of. When you calculate the mass of an object, it also gets mass from the energy inside it. So if there's energy inside an object, if you have to put energy into those Legos to combine them together to make a proton, then that energy also contributes to the mass of the object, right? E equals mc squared. So as you add energy to an object, it gains in mass. And so the mass of the proton is not just the mass of the stuff that makes it up, but also the energy of those objects. And that energy is represented in particle form in terms of gluons, these massless but very energetic particles that are whizzing around between the quarks.
Yeah. So the proton is not just a simple like three building blocks stuck together, three quarks. It's like it's got this weird sort of quantum mechanical sea, a frothing sea of other particles also holding the whole thing together. And so let's get into what that sea is made out of, how exotic it is, and how we know what's going on inside of the proton. But first, let's take a quick break.
It's crazy how much we have to pay for outdated, impersonal healthcare, and even crazier that we all just accept it. It's time to face facts. Healthcare is backwards. Luckily, there's Forward, a new approach to primary care that's surprisingly personal and refreshingly straightforward. Forward never makes you feel like just another patient. Backed by top-rated doctors and the latest tech, Forward gives you access to personalized care whenever you need it. Using in-depth genetic analysis and real-time blood work, Forward's top-rated doctors provide you with in-depth insights to better understand your genetics, mental, and physical health. They then create custom, easy-to-understand plans to help guide you to achieving long-term health. With Forward, you get unlimited in-person visits with your doctor and access to care anytime via the Forward app, all for one flat monthly fee. It's time to stop accepting backwards healthcare and start moving your health forward. Visit GoForward.com today to learn more. That's GoForward.com.
Lately, I've been itching for a getaway, a chance to unplug, rest, relax. If you feel the same, then listen up. You can go from daydreaming to sunbathing with the American Airlines Advantage MileUp card from Citi. With it, you can earn Advantage miles on everything you buy. You'll also earn 2 times miles at grocery stores and on American Airlines purchases. Miles that can be redeemed for flights, hotels, and so much more. Plus, you can even earn 10,000 Advantage bonus miles and a $50 statement credit after qualifying purchases. Book me a one-way ticket to a beach chair, please. If you're looking to get closer to that next getaway, head to Citi.com/MileUp today to apply for the American Airlines Advantage MileUp card. That's Citi.com/MileUp.
There's games you play alone. Then there's games that bring you together, forging friendships out of friendly competition. June's Journey is one of those games. 30 million fans have downloaded June's Journey, putting their detective skills to the test. Why haven't you? June's Journey is set in the roaring 1920s, and your mission? To help June Parker solve the murder of her sister. She suspects foul play, and it's your job to prove it. Seek and find all the hidden pictures in time, play Spot the Difference, and compete with friends to see who has the keenest sense of observation. There's something for every amateur detective. Each scene is beautiful, colorful, and carefully crafted to make you feel like you're literally stepping back in time. If you love the glamour of the 1920s, love solving mysteries, and love climbing the leaderboard with new friends, then download June's Journey today. It's the most fun you'll have on your phone. Available for free on your favorite app store and on desktop through Amazon and Facebook.
All right, we're talking about what's inside the proton. And Daniel, I assume it's not bananas and ice cream?
Metaphorically speaking, yeah, it is kind of bananas in ice cream. I mean, we talked in the beginning of the podcast about how, mostly the proton is up quarks and down quarks. And that's sort of conceptually true that it's mostly that. But from an accounting point of view, it's mostly not, right? Most of the proton is this C. Most of the mass of the proton comes from the energy of these gluons. So actually, you can sort of ignore the up quarks and down quarks and say that mostly the proton is just like a seething mass of gluons.
Right. Well, this is kind of a difficult concept maybe for a lot of people who might be listening to this, is we're saying that the mass of the proton is mostly the energy that it takes to bind them together. But then you're saying that this energy sort of exists as gluons that are kind of popping into and out of existence. Is that what you mean? Or is that mass sort of just in the potential energy of holding these quarks together?
Yeah, that's sort of a deep philosophical question. People are divided about how to think about it. One way to think about it is that you have the real objects, the up quarks and the down quarks, and they have these strong forces between them, strong with a capital S, like the strong nuclear force. And those forces can be represented in two different ways. One is as a field. You say there's a lot of energy stored in the quantum field of the strong force inside the proton. So some people think of it as particles, and the energy is the fields. And from that point of view, you could also think of the up quarks and down quarks as just part of the up quark and down quark fields. So you think of it it's all fields, right? The forces are fields, matter is fields, just energy stored in quantum fields. There's another way to think about it in terms of the particles. You say, the particles are the real thing. Up quarks and down quarks inside the protons are particles. And then what about the forces in between them? Well, you can also think about those forces in terms of particles. And so when we say the energy is stored in the form of gluons, what we mean is that the strong force, which holds all these particles together, is exchanging gluons. The energy of the strong force is used to make these virtual gluons, which whiz back and forth. It's just another way to think about how to account for that energy. Is it in the fields? Is it in these virtual particles? Mathematically, it's sort of equivalent. Philosophically, it makes you think about it conceptually differently.
Because I imagine gluons, they're not theoretical. They have a mass to them, right? Gluons have mass?
Gluons do not have mass, but they are not theoretical. They are a real thing. But gluons are massless, just like the photon.
But they have energy to them, right?
They have energy to them. And so they move at the speed of light, just like photons do. And just like photons, they have energy, right? Photons can have energy even though they have no mass.
Right. But mass is energy. So I'm sort of right? Sort of?
Well, it's especially complicated because photons don't have internal energy, right? Mass comes from internal stored energy. And a photon doesn't have any internal stored energy. You look inside a photon, there's nothing there. All it is the motion. So you don't get mass from having energy of motion. You get mass from having internal stored energy, which is why you can weirdly have a photon that has energy but no mass. And also, if you want to go there for those listeners really into the details, the full equation for E equals mc squared has another term to it. E equals mc squared, the m there refers to the rest mass of the particle. There's another term for adding momentum of the particle. And photons, of course, have no rest mass because they can't ever be at rest.
So there's some fine print there. So then maybe can you give us an explanation of how these gluons or how this kind of stored energy gives something more mass? Is it that if I try to push a proton, I also have to sort of create these gluons interacting between the quarks, and that takes some energy. And so that's why it's harder to push the proton?
I wish I could, but it's not something that physics really understands. It's just something we sort of describe. We notice that if you have more energy stored inside something, it has more inertial mass. This is something we observe and describe. We do experiments. We see that if you add internal energy to something, then it takes a larger force to accelerate it. So somehow there's a property of internal stored energy that it has inertia, right? That energy takes a force to move it around. And I wish we had a deep fundamental understanding of why that is, but it's just something we sort of observe about our universe and describe.
It's a massive mess to try to wrap your head around.
It is. You have intuitively sort of an understanding of why objects that have mass take a force to accelerate them, right? If you want to push on a really big rock and get it going, it takes a big force. It's sort of hard to wrap your mind around why, if you give that thing internal energy, if you make the rock hot, why should it take a larger force to accelerate it, right? But that's because you think of the rock in terms of the stuff inside of it. But really, mass is not a measure of the stuff inside of it. It's sort of more like an indicator of how much energy there is inside something. That's really what mass is. It's like a dial that tells you how much energy is stored inside this thing, either in terms of the masses of the particles it's made out of or the energy between them.
So then all this extra mass I've gained this summer, it's really just energy is what you're saying.
You could probably turn it into lots of energy to go for a long, long jog. Yeah.
All right. Well, but you're saying one interpretation of this extra energy that's stored inside is as a sea of particles, meaning like there's a frothing kind of quantum sort of volume where particles are popping into and out of existence.
Yeah, every time two quarks interact with each other, they're buried deep inside these like bound states of the strong force. Every time they interact with each other, you can think of it like they are passing a gluon back and forth. The same way you can imagine like what happens when two electrons repel each other is that they use a photon, because a photon carries the electromagnetic force, a gluon carries the strong force. And so when two quarks interact with each other, they're passing a gluon back and forth. And so that means that the best picture of what's inside a proton are like three tiny little dots and then a huge swarm of these gluons going back and forth between and around all those quarks.
Right. So then they're creating gluons and then the gluons turn into other particles, right? That's where this weird sea of particles comes from.
That's right, because gluons don't just hang out. They're very energetic. And they fly through space, and they are quantum objects. And when they fly through space, they have a lot of options for what they can do. They can just stay a gluon, do nothing. That's sort of the most boring, most likely thing. But they can also turn into pairs of particles, like the same way that a photon flying through space can momentarily turn into an electron and its antiparticle. A gluon can do that also. A gluon can turn into a quark and an antiquark. It can also turn into two gluons. Like gluons feel the strong force themselves. That's part of the reason the strong force is so strong, because gluons make more gluons, which make more gluons. And so these gluons don't just fly through space simply. They create this flickering blob of virtual other particles, quarks and antiquarks, all the time.
So then is the idea then that the three quarks inside of a proton, they're constantly interacting with each other, even though they're just sitting there, they're constantly in a sort of quantum mechanical virtual way, exchanging gluons all the time. And those gluons are creating other particles. So there's like a virtual party all the time inside of a proton.
Exactly. The same way that like an electron flying through a field is surrounded by a swarm of photons, and those photons are turning into like other pairs of particles all the time. So every particle is actually surrounded by a little frothing virtual mass of particles, but especially where there's a lot of energy. And so you're exactly right. These quarks are constantly interacting the same way like a proton and an electron, which makes up hydrogen. Those two things are bound together, which means they are interacting. They're held together by their electromagnetic force. In the same way, quarks are being held together. So they're interacting constantly. And the gluons that are passing back and forth between them don't just stay gluons. They turn into all sorts of crazy particles all the time.
Right. So then that's sort of the answer to the question of what's inside a proton is that there's quarks, two up quarks, one down quark, and also a whole bunch of other particles like gluons and all these other crazy particles that gluons turn into.
That's right. And that's sort of the other side of this story, that we discovered that mostly we are made out of a few simple particles, up quarks, down quarks, and electrons. But there are other particles out there. In our collider experiments and in cosmic rays, we discovered weird particles, muons and taus and other quarks, strange quarks and charm quarks and bottom quarks and top quarks. And we thought, well, what do we need those for? We don't really need those to make up ourselves, to make up ordinary matter. But actually, it turns out that those do play a role in matter, because when the gluons are flying around inside the proton, they can turn into any of those particles. They can turn into a pair of quarks, right? Any quarks, even bottom quarks, even top quarks. So that means that the proton has inside it not just up quarks and down quarks, but a little bit of everything.
A little bit of everything. Everyone's coming to the party.
That's right. It's like when you go to the kitchen and you just sort of like take all the spices and you put them inside your dinner. Like that's what the proton is. It's a little bit of every flavor. It's an international potpourri.
And I guess it's not just the proton. I mean, any one of these sort of composite particles that are made out of multiple quarks, maybe they're also a big party in themselves.
Yes, exactly. Neutrons have a very similar story. And even particles that we think are fundamental, right, like the electron, is surrounded by a swarm of virtual particles. Even when it's not like bound into a hydrogen atom together with a proton, it's still interacting. It still has an EM field around it, which means photons. And those photons are doing the same thing these gluons are doing. They're turning into muons and taus and quarks and all sorts of crazy stuff all the time. So there's some cool consequences of that, right? It means that these particles don't just have matter in them, because when a gluon turns into quarks, it can't just like create quarks out of nothing. It has to, at the same time, create anti-quarks, right? Like a gluon can become up anti-up, or bottom anti-bottom, or top anti-top. So what that means is that inside every proton, there's also antimatter.
Whoa. But then wouldn't that antimatter touch regular matter and then explode?
It does, exactly. So what happens is the gluon is flying along and it turns into a particle-antiparticle pair. And then very quickly, those two annihilate back into a gluon. And that's what happens when matter meets antimatter. It turns into a gluon or a photon or some other kind of energy-carrying force particle. If you have a lot of it around, then it very quickly turns into a lot of energy, and that's very dangerous. Here, they're just turning sort of back into the gluon or back into the original photon they came from.
I think what you're saying is that it's a pretty good party inside of a proton.
There's definitely stuff happening.
All right, well, let's get into how we actually know what's going on inside the proton and what it could all mean for our understanding about particles and what we're made out of. But first, let's take another quick break.
Millions of Americans are getting back to work. CareerBuilder calls it the great rehire. And we want to help you get the best jobs before everyone else. CareerBuilder gives you the competitive edge to get the job you want, at the salary you want, with the benefits you want. We even send job alerts, so your perfect job lands right in your inbox. Go to CareerBuilder.com today, or get left with whatever jobs are left. Find your next job fast at CareerBuilder.com.
To show you how easy it is to file a claim with Geico, we hired a soap opera star.
Gracious me, my car has storm damage and I've had to file a claim. Could it possibly get worse? Will my claims team leave me for someone else? Someone less intense?
No. Actually, when you file a claim with Geico, you get your own dedicated claims team who promises to stay with you throughout the process.
Oh, I've never known such loyalty. I can't wait for the second season.
Geico. Great service without all the drama.
Good afternoon. Would you like to try a free sample of our double fudge brownie?
Oh, sure. That's very good. I'll just take one more, just to be sure. Yep, still very good.
Some things never change, like never being able to take just one free sample. And Geico saving folks lots of money on their car insurance.
Is that macadamia nut I taste? Let me take one more.
Sir?
Yeah, I thought so.
15 minutes could save you 15% or more.
Right, Dan, we're talking about what's inside of a proton, and it's a lot. It's not just a couple of quarks. It's not just two up quarks and a down quark. It's also this virtual sea of quantum particles popping into and out of existence, gluons turning into antimatter and other kinds of particles. I guess a big question then that a lot of people might have is, how do we know this thing? Is this something like we know out of theory, or have we actually observed this crazy party inside of the proton?
Yeah, we have actually observed this crazy party. We know that you and I are all made out of all this stuff, including antimatter. And, you know, I remember learning this fact that like, whoa, I'm partially made out of antimatter. It made me sort of feel different about like who I am, you know, and what I'm made out of. I really thought myself as solidly in the matter category. Now I felt like, ooh, those lines are blurred a little bit.
It's like when you grow up and you start to have more conservative values and leanings. You're like, whoa, what's going on? What's going on inside of me?
Yeah, exactly. I won't say which political side of the spectrum is matter and which side is antimatter, but exactly. Everything turns out to be more complicated when you grow up. Welcome to adulthood. You're partially made out of antimatter. But yes, exactly. There's a long series of experiments here dating back to the early 1900s that have allowed us to probe what's going on inside our bodies. And as usual, you have to be really careful with the question you are asking. Like, what do we mean when we say we're made out of this stuff? You know, because in science, you can only do experiments. You can't talk about like what's there when you're not looking at it. You can only talk about what are the results of experiments you can do. And here specifically, there's only one kind of experiment we really can do, which is basically shoot particles at something and see what it bounces off. So when we say, for example, what's inside a proton, what we really mean is what happens if we shoot particles at a proton, what does it bounce off of? And we know that mostly it bounces off of up quarks because there's two of those in there. And sometimes it bounces off of a down quark. And when we say there are gluons and top quarks and taus and all sorts of stuff inside the proton, what we mean is that sometimes when you shoot a particle at a proton, it bounces off of a top quark or bounces off of a tau. And so this comes from a long line of really fascinating experiments, beginning with Ernest Rutherford, who did this kind of experiment in the early 1900s. He was the one that discovered that like the atom has something inside of it called the nucleus. He shot alpha particles at a sheet of gold and saw that occasionally these things bounce right back, meaning that he found like something hard inside the nucleus to bounce these particles off of. And everything we've been doing in particle physics for the last 100 years is basically an extension of that one experiment, but zoomed in a little bit. So like in the 1960s, we did these experiments called deep inelastic scattering, where we shot electrons into the proton. And what we saw there was that there were sort of three hard nuggets you could bounce off of. And those were the quarks. That's how we know that there are quarks inside the proton. If you shoot really high energy electrons inside them, they sort of bounce back from three specific points.
For real? Like you can take a picture of inside of a proton, kind of, right? Like you shoot a bunch of particles, electrons at it, and you sort of get an image on the other side. You're saying that you can actually see these hard nuggets of the quarks inside of it.
Yeah, it's sort of like taking an image. Unfortunately, you can only shoot one particle at an individual proton. So to really image it the way you're describing, you would have to shoot like a lot of particles at a specific proton, like hold it in place or something. We can't do that because once you shoot one electron at a proton, it blows it up. You just get one measurement. But statistically, we can do it many, many times over many protons and just like count the number of electrons that bounce back, that indicate they hit something hard versus the number of electrons that like went right through. That indicates that they sort of missed all the good stuff inside the proton. And from all those calculations, then we can calculate like how many hard points are there inside the proton. And so that's the same basic thing that Rutherford was doing basically 100 years ago. But now we're just like doing it with higher energy, and we're doing it to the proton instead of doing it to the atom.
So it's sort of almost like an X-ray of the proton, but you have to do it in bulk.
Yeah, you have to do it in bulk. And what we can do are specific calculations for like what would happen if there were also a little bit of bottom quark inside the proton? And what would it look like if there was occasionally tau particles inside the proton? Because these particles are all different, they all would give like a different reaction spectrum from the electrons you're using to shoot inside there. So that's like one way we can get a sense for what's inside the proton. We're like X-raying it with electrons, as you said.
All right, so that was in the 60s. So what's sort of the cutting edge right now in terms of looking inside of the proton?
So people really want to understand in detail what's going on inside the proton in terms of how much antimatter is there. It's really sort of exciting and cool to think that there is antimatter inside of us, and we want to understand how much antimatter is there and what kind is it specifically. And most interesting, people want to know, like, is there more anti-up quarks or anti-down quarks inside the proton, or are there the same number? We figure like, a gluon has the same chance to turn into an up anti-up pair as it does to turn into a down anti-down pair. So there should be the same amount of anti-downs and anti-ups inside the proton. So those are the kind of questions people are asking now. And there's a new experiment been going on for the last couple of decades that's trying to understand exactly the antimatter component of this sea of gluons and stuff inside the proton. And so the experiment is called SeaQuest.
That's a pretty cool name. Sounds like a TV show or like a 90s cartoon.
It is the name of a TV show. And I don't know if the experiment or the TV show came first, but this has nothing to do with the ocean of water, right? It's like thinking about the ocean of gluons. And so this is a very different kind of sea than like underwater science fiction adventure.
Right, although technically water is made out of protons, which has a sea of particles too. So really, all quests are SeaQuest.
You're right. We're all from the ocean originally. And so this experiment is a little bit different from the ones they did in the 60s. Here, what they're doing is they're taking the proton itself and they're smashing it into other stuff. One reason for that is that they're doing this experiment at Fermilab, and Fermilab is a place that's good at accelerating protons. We used to have the largest particle accelerator in the world there called the Tevatron, where the top quark was discovered in 1995. So they're very good at making protons and accelerating them. So they decided to sort of reuse that and smash protons into stuff to see sort of what they turned into. The original experiment was like X-ray the proton by shooting electrons at it. Here it's like take the proton and smash it into stuff and see what comes out and try to deduce from what comes out what's inside the proton.
Right. And so what have they found?
So they've been doing these experiments where they shoot protons at two different kinds of stuff. One is a target just of hydrogen, which is basically pure protons. And another is a target with deuterium, which is a combination of protons and neutrons. And now neutrons have a different mix of up quarks and down quarks, right? They have more down quarks than up quarks, whereas the proton has more up quarks and down quarks. So by shooting it at hydrogen and then shooting at deuterium, you can get a sense by looking at the ratios for like how much down quarks there are and how many up quarks there are. So they smash protons into these two different targets, and sometimes a quark in the proton in your beam interacts with an anti-quark in the target. So for example, maybe an up quark in the proton you're shooting from your beam interacts with an anti-up quark inside the neutron or inside the proton. And when that happens, you can tell because it creates a photon because they annihilate. And that photon sometimes creates like a muon and anti-muon. And that's what this experiment looks for. It looks for these pairs of muons and anti-muons coming out of these collisions. And by looking at those muons and their energies, they can get a sense for like, oh, did we hit an anti-up quark or did we hit an anti-down quark? And so people expected to see the same amount of anti-down quarks and anti-up quarks inside the proton. But what they found is that there's actually a lot more anti-down quarks than anti-up quarks. There's like 40% more anti-down quarks than anti-up quarks inside every proton.
I think this is where it gets confusing because you're saying anti-ups, and I'm thinking anti-up is just down. But that's that's different than anti-down, which is not up.
Yeah, exactly. It's anti in a different way. That's the sort of confusing but also awesome thing about particle physics is that there are all these reflections, right? You're right that the up and the down are reflections of each other, but in sort of like a different direction than the anti-particle way. And there's other reflections, right? Like the charm is like another reflection of the up, but in terms of particle flavor. So there's like this multi-layers, many-faceted symmetries in particle physics can be hard to keep track of.
Right, but I think what you're saying is that this experiment sequence is smashing protons, and it's trying to determine sort of the amount of antimatter inside of these protons. And the weird thing is that you're seeing a lot more antimatter of the kind that comes from down quarks than from the antimatter that comes from up quarks. And that's weird.
That's weird. It's not what we expected. Yeah, we expected sort of a balance there because, where does the antimatter come from? It comes from gluons, from photons flying around inside the proton. It only exists briefly. And we think that those gluons should have the same chance to create down quark type antimatter as up quark type antimatter. Why would they prefer one to the other? That's really strange. And it's a clue that something else might be going on, something we don't yet understand. So it's a nice little like thread to pull on to try to unravel some of the other mysteries of particle physics.
I guess the weird thing is that it likes one kind of antimatter and not another kind of antimatter. Is that what you're saying?
Yeah, it likes them both, but it likes one 40% more.
And so that's a pretty interesting mystery. But what does it all mean? What does that tell us about what's inside of the proton?
Well, it's interesting because the proton, as we learned, is mostly gluons, right? It's mostly this energy from the strong force. So if you want to understand what's inside the proton, meaning what you and I are made out of, you really have to understand the strong force. And this is something we've been struggling with for decades since we discovered the strong force. It's very weird and very hard to understand. And one reason is because it's so strong and it couples to itself, right? Like gluons, they feel the strong force themselves. So every time you create a gluon, you're creating the chances for more gluons. And then those gluons can create more gluons and more gluons. The same is not true for photons. Like photons do not feel electromagnetic forces, right? Because they do not have a charge. It's sort of like if the photon had +1 or -1 electric charge and it like created its own electromagnetic fields and crazy stuff like that. So the strong force is very difficult to deal with because anytime you do a calculation, you instantly have to account for like infinities and infinities of gluons. So we don't really know how to do calculations using the strong force. It's much harder than calculations for electromagnetism. So we can't answer simple questions about what would happen if you put together quarks into a proton, which means that we need to look into nature to see what actually happens and use that as a guide to say, well, how should we build our theory? What's going on with the strong force? So to get a better understanding of the strong force, we can't just like think about it inside our heads and do computer simulations. We need to like actually go out into the universe and see what it's doing.
I think you're saying that looking inside of the proton and discovering all these virtual particles and these gluons turning into other things is sort of our window into how these basic forces behave. And it's kind of our into understanding how they actually work.
Yeah. We are watching them at work because we don't understand how they work. And so by watching them, hopefully we can get ideas and glimmers for what's going on and how to describe these things. You know, we have a mathematical tool for describing the strong force, but it doesn't work very well. We can't use it to make predictions and calculations. It's sort of like impossible to use. It's like if somebody told you how to calculate something, but there was like an infinite number of steps. You say, well, that's not very useful. I can't use that to do any calculations. And so if we want to understand these things, you're right, we have to look at them in action. We have to watch them actually happen and hope to observe some trends, some ideas, which can help us come up with a better model, one we can actually use to play with theoretically and understand how these things work.
Well, then what's on the horizon? I know this experiment found an interesting mystery, but are there any other experiments sort of looking into what's inside of the proton?
Yeah, so these guys found an interesting mystery. And I love this experiment because they're sort of like a scrappy bunch. They don't have a lot of money, so they like repurposed stuff from other experiments. You know, like they used old scintillators left over from another lab and old particle detectors left over from another experiment and iron slabs used from the 50s in Columbia. And so they sort of like build this experiment from spare parts, which is really pretty cool. And they're doing it again. They're making a new experiment called SpinQuest. SpinQuest is going to reuse most of the same parts, but it's going to probe even deeper and try to understand another basic question about the proton, which is why does the proton spin have the value that it does? We can't understand the spin of the proton from the spin of the quarks. The same way we can't understand the mass of the proton just from the mass of the quarks. There's the same kind of question about the proton's spin. So they're going to do an experiment to try to understand where the spin of the proton comes from with the same people and the same reused parts.
Interesting. So like the spin of the proton is like the sum of all of the spins of all the things inside of it, which is a lot, which is a big party.
Yeah, it's not just from the spins of the up quark and down quarks. Those gluons and photons also contribute to the spin of the proton. So if we can measure the spin of the proton really accurately, we can try to get another handle for what the proton is made out of, what this mystery cake that we're all built out of, how it was actually cooked.
Right. What are all these exotic flavors I'm tasting?
That's right. I thought I was pretty vanilla. It turns out I'm a little spicy.
It's a lot of tiger flavors in there. And I like how you're like sitting on top of your LHC multi-billion-dollar experiment and looking at these other experimenters coupling together with spare parts and calling them cute.
Yeah, you know, this thing only costs a couple tens of millions of bucks. What a fun little experiment, just like a Saturday project.
All right. Well, I think the main takeaway, though, is that we are not as simple as we thought we are. Even though we're only made out of quarks and electrons, those quarks that make up the proton, there's a lot going on in there. It's not just quarks inside of our protons and neutrons. It's also all these crazy exotic particles, virtual particles popping into and out of existence, influencing how much we weigh and how much mass we have. And there's also a lot of antimatter inside of us.
Yeah. So these exotic particles that we discovered in cosmic rays and in colliders are not just an intellectual curiosity. They're not just clues about the organization of the universe. They are also part of me and you. They are part of the definition of what it means to be a proton, which is the basic building block of everybody and everything and every dinner you have ever had.
So exotic is the new normal. That's what you're saying.
That's right.
We're all exotic.
That's right.
So nothing is exotic?
Yeah, well, we have all enjoyed eating antimatter, for example. So I don't know if that counts as exotic.
I'll give it an anti-review. I'll give it an up review, which is really an anti-down review, which is actually a good thing, right?
That's if particle physicists had built Yelp, there would be all those options.
up, down, anti-up, pro-down, all of them.
I'm down with that if you're up for it.
Yeah. And you can give it a 5 to an infinite number of stars.
Yep. Fractional stars.
All right. Well, we hope you enjoyed that and got you to think a little bit more about what we're made out of, what you're made out of, what that banana you're eating is made out of, what the stars are made out of, because it's a much more interesting story than we think it is.
And the story continues. In this arc of understanding what we are made out of, we have discovered many surprises along the way, and I'm sure there are many more to come.
I'm just glad this podcast wasn't boring, even though you're at the Niels Bohr Institute.
Yeah, exactly. I hope that it's annealed your understanding of the non-boring nature of the proton.
Oh, man, that was an extra nerdy pun there.
I tried to put a little Danish on it.
All right. Well, enjoy your bath there in the bathtub, Daniel. We'll talk to you next time. We hope you enjoyed that. Talk to you later.
Thanks for listening, and remember that Daniel and Jorge Explain the Universe is a production of iHeartRadio. For more podcasts from iHeartRadio, visit the iHeartRadio app, Apple Podcasts, or wherever you listen to your favorite shows.
Did you know that we made the free iHeartRadio app so you can listen to hundreds of thousands of podcasts anytime you want, anywhere you want, totally free? Love music? Us too. We use music for everything we do in our lives, and the free iHeartRadio app has playlists with music perfect for every mood and every moment in your day. So we thought we'd share those with you too. Add to that being able to stream your favorite radio stations from anywhere. It's all free on iHeartRadio. #1 for music, radio, and podcasts. All in one app.
I want to get back to kissing the cheeks of my grandbabies, making Sunday dinner with a house full of family and lots of laughs.
COVID-19 has changed how we live and how we feel. But now, there are vaccines. And they are the very first step that let us get back to what we miss most. It's okay to have questions.
Is it safe?
Should I wait? Now, get the facts. Visit getvaccineanswers.org so you can make an informed decision when vaccines are available to you. Brought to you by the Ad Council.
The stories that are affecting the Black community are being covered on the Black Information Network. Not a show or a podcast, BIN is a 24/7 news network covering stories from a Black perspective. Listen to the Black Information Network on the iHeartRadio app and get news for and by the Black community. Anywhere, anytime. Keeping you informed, keeping you engaged. The Black Information Network and BINnews.com.